Okay, guys, let's try to do problem number 3, a hanging mass. In this case, we have a 2-meter long horizontal rod of negligible mass. So I'm gonna just draw the scenario. Here's my rod, and it's mounted to a wall with a hinge. So I'm gonna just put a hinge here on the left hand side and a cable on the right end angled at 45 degrees above the horizontal. A sign of mass 50 kilograms is hanging from the center of the rod. What is the tension of the cable? And what is the vertical and horizontal components of the hinge force? So for part A, let's draw a free body diagram. So let's draw a box that's going to represent our sign. The force that it's feeling straight downwards, its weight. We also have the tension at a 45-degree angle. And we also have the hinge force. So I can imagine the hinge force is always going to be pointing opposite to the tension. So if the tension is pulling up this way, the hinge force is going to pull it opposite to that. So that's how I'm going to draw my hinge force. I'm just going to put F for force. This should be all the forces that this mass is experiencing. So let's talk about what tensions the mass is experiencing, or sorry, what torques. We have the torque from the sign itself, and we also have the torque from the cable. And if this is a rotational equilibrium problem, I could just set these two equal to each other. And that's going to come in handy to find the tension of the cable. So first, let's find the tension of the sign. Remember, the equation for torque is the force times the distance times sine of theta. In this case, the weight is the force, so the weight times the distance times sine of theta. And in this case, the weight would be 50 kilograms times the acceleration due to gravity, 9.8 meters per second squared. Although the rod itself is 2 meters long, the actual weight is only at 1 meter distance from the pivot point. So 1 meter, and sine of theta in this case is not 45. The angle that the weight is making with the rod is 90 degrees. So that's what we're going to use. We're going to use sine of 90 degrees. And as you know, sine of 90 degrees is just 1. So times 1. If we multiply all that out, 50 kilograms times 9.8 meters per second squared times 1 meter gives us 490 Newton meters. remember Newton is a kilogram meter per second squared, and we have a meter, Newton meter. Now the torque from the cable or the tension is going to be the tension force times the distance, in this case is 2 meters, times sine of 45 degrees. And we could set that equal to the tension of the sine, 490 Newton meters. And then all we have to do is solve for the tension of the cable. So tension of the cable, if we divide both sides by 2 meters sine of 45 degrees, that leaves us with our result, 490 Newton meters divided by 2 meters sine of 45, leaving us with 490 newtons divided by 1.414, which is equal to 346.3 newtons. And that is the tension of the cable. We're going to go ahead and do part B in a separate video because this video is getting a little too long.